some of the esteemed faculties of the Indian Institute of Science, Education and Research, Kolkata, will discuss the research areas of the Nobel laureates this year. So this time, this is the very first episode, which is the talk one or episode one of in the subject of physics. And now I would like to hand it over to today's host, who is Tanishtha Roy. Tanishtha, are you there?
Yes. Am I audible?
Yeah, you are completely audible. Okay, so you can continue from here. Thank you.
Thank you, Shayantan. The honorable speaker for today's talk is Dr. Amit Ghoshal. Dr. Ghoshal is an eminent researcher hailing from the Department of Physical Sciences in the Indian Institute of Science, Education and Research, Kolkata, who completed his PhD from the Tata Institute of Fundamental Research, Mumbai. His research work focuses primarily on condensed phases of matter, in which the complex interplay of interparticle interactions and intrinsic disorder in the material leads to intriguing emergent phenomena. He will be helping us understand the work of the Nobel laureate Giorgio Parsi on complex systems. So today's discussion will focus on one of the topics which led Dr. Parisi to the roadway of Nobel Prize in Physics 2021, which is the interplay of disorder and fluctuations in different physical systems. But before that, let's have a glimpse of the research background and the exposure of the Nobel laureate's field of working. Giorgio Parisi is an Italian theoretical physicist whose research has focused on quantum field theory, statistical mechanics, and complex systems. He was awarded the 2021 Nobel Prize in Physics jointly with Klaus Hasselmann and Syokuro Manabe for groundbreaking contributions to the theory of complex systems, in particular for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. Giorgio Parisi discovered hidden patterns in disordered complex materials. This discovery makes it possible to understand and describe many different and apparently entirely random materials and phenomena, not only in physics, but also in mathematics, biology, neuroscience, and machine learning. He also believes in the values of asking questions, basic questions, and also said in an interview that we should work on a problem only if the work on that problem is fun. Before we just start, we'd like to mention that you may post your questions and doubts in the chat box, and the audience watching the YouTube live can also pose their questions in the live chat. Hoping for a spectacular interaction with you all. And now we would like to hand it over to today's honorable speaker, Dr. Amit Ghoshal. Please, sir.
Thank you, Tanista, and thanks, Shayantan and other members of Science Club. This is a real honor to try to say something on the research work by Giorgio Parisi, who is the recipient of the uh, Nobel Prize in Physics 2021. So let me quickly, I see some different screen here, Nobel Talk series. So let me try to uh, get to my slide. So let me know if that is visible to you all. Is it visible now? Can you confirm?
Yeah, sorry, it is visible. So I will just remove my presentation from the screen. Just a second.
Okay.
Yeah, it's fine.
Okay, so great. So thanks again. And I must say that I'm not from the same field in which Giorgio Parisi works. Certainly I work in disorder physics, but that's somewhat different from what uh, the area of Giorgio Parisi. So it was a wonderful experience for me to try to learn some of the stuff that he has done. So I'll be talking about that mostly. Thanks again. Okay, so let me go. Yeah, so on 5th of October 2021, Nobel Prize in Physics was uh, just let me. What happened? I can't get my. Okay. Mhm. Uh, So the Nobel Prize was announced for the groundbreaking contribution for understanding of our understanding of complex physical systems. So that's a quote. I mean, that's what Nobel Committee announced. So this was given to the award. It was awarded to three physicists: Manabe, Hasselmann, and Parisi. So the first two gentlemen, they received it for their pioneering contribution is in physical modeling of Earth's climate and reliably predicting global warming. So that's the statement that Nobel Committee had for these two physicists who received half the prize, who shared between them half the prize, and the other half of prize went to Giorgio Parisi, for whom the citation read. I mean, what is essentially the topic of today's presentation, that for discovery of the interplay of disorder and fluctuation in physical system, which is probably written here, fluctuation in physical system from atomic to planetary scale. So that's essentially the title of the talk, maybe slightly shortened version. So this is the picture of Giorgio Parisi. So very brief biography. So he was born in Rome on 4th of August 1948. So he is now 73 years old, and he did PhD from University Roma La Sapienza. I mean, that's where he is now as a faculty. His research area for PhD was high energy physics under Nicola Cabibo, and then he, as a professional, he was a researcher for 10 years into some institute, and then he moved to University of Roma to Tor Vergata, I mean, which is for his first tenure as a professor for about 10, 11 years. And since then, he is in University of Roma 1, which is La Sapienza, which is a very, very reputed institute, perhaps the most reputed university. I mean, it's more than 600-year-old, and I can tell more about La Sapienza, but that's not our interest. So he had been there as a professor since 1992. So he is quite a decorated physicist. Before the Nobel Prize, he got many others recognition, and all are signatures of some champion of physics. So, for example, Boltzmann Medal, Dirac Medal, and Italian Prime Minister's Medal, Enrico Fermi Prize, and Galileo Prize, and whatnot. So before Nobel Prize was conferred to him, he was already very, very popular, and there's no wonder, not even wonder. I mean, it is well known that his name was in the rumor mill for a probable Nobel recipient for last several years. So it was just a matter of time for him to get the prize. I mean, so it is. So the question is, what is it that made him such a eminent physicist and strongly probable candidate for the Nobel? So this is what we are going to dive into for today's talk. I mean, so it is like a scientific summary of what this talk is. Okay, so let's go into this slide, which writes complex systems. So as I said that the prize was awarded, I mean, all the three recipients are part of what is called complex system, study of complex system. This is the first time the study of complex system is recognized for a Nobel Prize, so which is a big thing. And this is also a very interesting thing, because when you hear the name complex system, there is essentially no jargon. I mean, you essentially understand what it means. I mean, we have from simple English, we have some comprehension for complex system, and the complex system in physics is not too different from there. I mean, which is not always the case. I mean, the field of physics is very, very specialized, and then you'll have prizes in different areas whose name are such that you might understand individual word, but together they make very, very special sense, which is accessible to physicists. So complex system is actually not. So there, the work of all these three gentlemen actually allowed us to derive conclusion about system that on the surface look random, they're unpredictable, and quite difficult to model theoretically. So here is a big area of complex system which is partitioned into various different things. So rather than, I mean, you can read the primary thing. I mean, and I can't read all the small things written there, but collective behavior. I mean, these are mostly in physics, and then there are network problems like neural networks, some very complex network that can consist that can qualify as a complex system. Then evolution and adaptation. I mean, that's more of a I mean, biological area where complex system and I mean, study of complex physics or complex system is very common. Then there are pattern formation, which is an interesting area. Like you see, there is a pattern. This is like a school of fish or some biological organism. I mean, whirling around in some region of water. So you want to understand the physics behind the formation of such pattern. I mean, so you do that, and then systems theory. Nonlinear dynamics is a very big area by itself, and I might touch upon just a little bit of that in connection with Paris's work. So that also qualifies certainly as part of complex system. Then game theory, this is more of a mathematical topic. So there is a very, very large number of possible systems which are considered as complex system. So what makes them special, or what makes them different? So unlike most other models or topics or areas in physics, complex systems are not a collection of just identical particles interacting in some regular manner or in an uniform manner. This is what we think of. So I mean, many of you might have read already, the model of an electron gas for a metal. So there we consider electrons which are all interacting in a Coulombic manner or some screen Coulombic manner. I mean, interactions are very similar in a pristine background where there is nothing else. So very regular. I mean, so that's what physics mostly deal with. Instead, complex systems are made of constituents potentially different from each other. They're interacting in different and unpredictable ways among themselves, and I'll explain that in a little bit. And then they're exposed to various different external conditions. So that makes it, everything is complex. So that way, as I said, it's a very, very simple physical meaning in terms of plain English that is good enough description. So there are many examples. So this is, I mean, so we showed some pictures. So here you can see this is like a flocking birds. I mean, they form some pattern. So this is a small movie. This you must have seen at various times. A bunch of birds. I mean, large collection of birds. They move around in a certain manner, producing different pattern. That could be a complex system. And finally, my students complain that my board work in class can be considered as a hotbed for describing complex system. Though I didn't quite agree with them, but okay, so that's a separate matter altogether. But then you get the idea of what made complex system and so on and so forth. So there are many examples, one of which we will take a detailed look into, and that is where the area where Paris's work is connected to. I mean, these are called spin glass, and we will talk about that. But here is just a picture of Parisi on the same evening of Nobel Prize announcement, October 5th. In Academia di Lincei, I mean, which is Rome. I mean, it's the biggest academy of science in Italy, and who is the president? I mean, Parisi is the president of that. So this is on the same evening. So what did he do in spin glass. So let's get into one representative. One representative area which is spin glass. So we will talk about that. Okay. Uh, uh, so 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 the stepping stone of modeling complex system is essentially, I mean, people start it in what are called disordered system, and this is part of the citation for the Nobel as well. I mean, we have seen. So spin glass is one prototype. I mean, you could call it a prototype disordered system. So what is this? What is spin glass really? So they are dilute alloy of magnetic atoms. So for example, you have largely, let's say, a copper atom in some kind of a crystal. I mean, so these are blue dots, which copper, and then you dissolve some fraction of iron atoms there, which are magnetic. So these are magnetic atoms in the backdrop of a matrix of a copper, as you see here. And so they could form a spin glass. So what happens is that these atoms which are coming with a magnetic moment, which are shown by this arrow, they point randomly in different directions. Okay, so which is shown here. So this must be contrasted with something which we call a ferromagnet. Uh, so where you have a lattice, which is, in this case, it is looking like a triangular lattice. So where every speed is pointing in the same direction. So this is what is called a low temperature phase. So you take a magnet like, iron or cobalt or nickel. If you cool them below some temperature called Curie temperature, they become ferromagnet, and that's their orientation. That's called a low temperature ordered phase. I mean, the order we will speak a little bit more, but you can see they're ordered because they're all pointing in the same direction. They're all aligned in some sense. So unlike them, if you take a spin glass, which is also a low temperature phase of matter, where the spins are completely misaligned, and not only that, spins are at very different distance between spins are very different. I mean, here they were made because it's a regular lattice. I mean, there was that that symmetry or coherence between the distance between spin. Here they're random. I mean, as you can imagine that, I mean, if you think of the location of these atoms here, the iron atoms, they don't form a regular pattern. So that way there is a disorder. Disorder is something which is random. That's the notion of disorder that we have. And so now if you think of the energy of the atoms meaning the one with an arrow, each atom is one with an arrow. So the direction, their energy depends on the direction of their magnetic moment. So the system is such that, I mean, this is defined, and we will do that more in quantitative manner soon in terms of model and so on and so forth. So if they're aligned, their energy goes down. And in physics, we know that the best situation or the ground state is the one where the energy is minimal. So at low temperature, for certain material, which are not spin glass, I mean, which are called ferromagnet in this case, there is a very nice ordered pattern of these guys, which is achieved. Instead, a spin glass, you have this random orientation, which will be your low temperature phase. I mean, ground state or not, it is a different question, and we'll talk more about it. But it is certainly a state where the system will survive for long enough time. So they are called glass. The glass comes because of the disordered or irregular nature of the distribution of these moments, which had a similarity with, let's say, the window glass, I mean, which is the silicon dioxide that we have. So in window glass or many other glasses systems, which are like supercooled liquid or structural glass, like there are many examples of glasses which are where you have an irregular pattern, just like you have spin glass that you see here in the actual silicon dioxide like window glass. Unlike, I mean, so these are quartz. I mean, this is what is called quartz. I mean, the same material, but with a very regular crystal structure. So this is the quartz crystal. So this is a crystal which is equivalent to a solid. I mean, you can say various things. You can say crystal. You can say solid. They are equivalent to the ferromagnetic case in case of uh, a spin world, whereas something like this, which is an irregular pattern, as you can see, sometimes you have a small distinct, sometimes you have a very large loop like that. So this irregular amorphous pattern, I mean, so this is another word which is often used for describing glass. So that will be equivalent to what is spin glass. So this is the glass state. So this is the low energy state of this material. I mean, they could go to quartz crystal, but more, I mean, depending on how you cool them at low temperature, they might land up being in a glassy state. So this is the description of a broader class of material which are called glass, I would say. And spin glass is a similar physics, but in terms of spin. Okay, so now spin glass is an area which is very important, and this was I mean, it doesn't require any certification from anyone, but Philip Anderson, who had been another very great physicist, I mean champion physicist, a Nobel laureate in the area of disordered system. So, and also he is, I mean, his name will soon appear in spin glass physics also. So he once mentioned, I mean, this is in Physics Today article, the history of spin glass may be the best example I know of the dictum that the real scientific mystery is worth pursuing to the end of the earth for its own sake. And then, independently of any other obvious practical importance or intellectual glamour. So this is a very strong statement, sort of certifying that this is a very, very important area of physics, and it indeed remained a very big important area of physics. And Parisi is involved in giving, I would say, a rather acceptable solution of the ground state of spin glass at low temperature phase. So he was able to describe that, and even more importantly, he developed a technique of how to describe these systems, which had far bigger implication because they could be applied to various other areas of a complex system, as we will see later. But let's stay for the moment on spin glass for a little bit more. Okay. So, by the way, if you have a question, I'll be happy to address them during the talk. I mean, it's not that I have a certain agenda to finish and so on. So please keep that in mind. But detailed question can be, I mean, particularly if you need clarifications, it will be fine to ask during the talk. I don't know exactly how that can be done, but yeah, so if that is required, I'll be happy to address those questions. Okay, so let's now get into a little bit more quantitative. So first, let's talk about what is known as Ising model. I mean, we call them Ising. I mean, we meaning I at least learned to call it an Ising model. Though I later learned that the actual name of the person is Ising. That's how it is pronounced. He is a German person. So in 1925, he came up with a model which looks very, very simple to describe what are these ferromagnets. Let's say, as I said, that there is something called paramagnet. I didn't show the picture. So there, paramagnet is a high temperature phase where all this ordering is lost. So that's the paramagnet, and then so these materials which are ferromagnet, as I said, that are below Curie temperature, if you cool a paramagnet, it becomes a ferromagnet. So that's a phase transition. So Ising was interested in describing that. So he came up with this model, and this is exactly to do what I said, that if these pins, I mean, so these I and J are indices of this lattice. So each point is I. So this is 1, 2, 3, 4, 5, 6. I mean, you number each of the lattice point as an integer, and I and J are those integer. So if you had to spin, and if the interact, sorry, I go in the wrong direction. So I mean, the interaction energy between the spin is such that if they are in the same direction, so this S are spin values. So you can I mean, you can take them to take you can consider them to take value plus minus one. I mean, so indeed what is done is that spin can be related to what is called a Pauli matrix. That is the one which will take value plus minus one as an eigenvalue. But let's not get into any more complication. Other than a constant, you can consider them to take value plus or minus one. Plus one if they are pointing, let's say, along this direction, upward direction, and minus one if they're pointing in the down direction. So this interaction will tell you that if they are pointing in the same direction, the energy will be 1 times 1 for that particular bond ij, and the energy will be minus j. On the other hand, if they're pointing to opposite directions, then this will be a minus sign here, plus 1 times minus 1, which will be minus 1, and then this minus will make it j plus j. So that is a higher energy than minus j. So that's the reason why I said that these magnetic atoms will like to align to gain energy, or that will gain energy, meaning the energy of the system will be lowered, and hence it will go towards ground state if they're aligned. Please remember that the fact that they are their directions are aligned and that will reduce the energy does not come from this model. It's basically because that happens in nature. You model it in some way, and this is what Isaac did. So to sort of match the description. And then Isaac asked, what happens if I lowered the temperature? Can I start from something which is, I mean, maybe I'll not. So you can consider them for the moment like a paramagnet at high temperature phase. I mean, spin can point in any direction. And then if I cool them, can I go into something like a ferromagnet? And then there could be other textures. So there are situations where if the spins in nearby sites, if they're anti-parallel, unlike being parallel, if the magnetic moment are anti-parallel, that can lower the energy. Such materials are called antiferromagnets. So you can have a transition from. So that will be a situation you can convince yourself where this sign will be flipped, and that will be a good model to describe this kind of ground state and so on. So now by tuning temperature, such a model shows the transition from a paramagnet to a ferromagnet. At low temperature, it will go to ferromagnet or antiferromagnet depending on the nature of the interaction. So now contrast this with a different model, which is Edwards-Anderson model. So Edward is Sam Edward analysis. Anderson is the same Anderson that we have mentioned here, the P.W. Anderson. So the only difference is, so there is one very crucial information here which I did not mention, is that here the I and J, the sides of lattice, they interact only when they are nearest neighbor. So like nearest neighbor meaning the one, I mean, from this side, the nearest neighbor will be 4, 1, 2, this is 3, and this is 4. Every side has 4 neighbor on a squared lattice. And similarly, you can construct other geometry of lattice and so on and so forth. So they're only nearest neighbor interaction. That means a spin which is very far, this spin does not interact with this one because they're not related to each other by a nearest neighboring relationship. So Edward-Anderson model is also similar model, except for the fact that Jij can take a random value. So random value meaning that for a particular ij, so the value of Jij is different depending on which pair or which link that you are considering. This link will have a different value of interaction strength J, that is called interaction strength, than what this link will have, than this link will have, etc. So they're completely random, but still the interaction is only between nearest neighbor. So that a model like that, where you have disorder and such a situation is called quenched disorder. So it's a disorder which is frozen on the system, meaning once for all you fix the value of J, and that doesn't change if you change temperature and so on and so forth. So the value of Jijs are fixed. They are random, on every different link. I mean, they're different from every different link, and they're random, and they are distributed. So whenever you talk about random, you have to sort of specify what kind of distribution does that Jij follow, and that distribution is, I should have put a picture, but it is called a Gaussian distribution. Uh, so it has certain form. I mean, this is an expression. If Jij was x, then it will have a functional form of e to the minus x squared, except for some constant here and there. So that's what is called Gaussian, and I expect I'm thinking that many of you would know what is Gaussian. So that is one model. So there is another model, and this seems to be very similar, but there is a slight difference. Here, ij are nearest neighbor, whereas they are not. It just say I less than j. I less than j is just a symbol to ensure that you don't have a self-interaction. The site I does not interact with site I itself. That's not possible. Ij are different, and Ij will be taken such that you are taking this summation over all neighbors or all independent link between any I and any j. So for a very large system, in this case, in this particular case, which is known as Serrington-Kirkpatrick model for spin glass, it was given at the same time. And please note that the Ising model, which is sort of a parent model from which all this study of this spin physics emerged. I mean, that started in 1925, whereas these models came in 1975. So it took 50 years for people to realize that it has a value to study systems with disorder. So that's a different story altogether. When people initially started studying disorder, people thought of disorder to have some kind of effect which will just make a fuzzy line instead of a sharp transition line. That's the effect of disorder. But soon with time, I mean, starting from mid-70s, and then people realized that disorder by themselves can produce very beautiful physics. And that is certainly, I mean, there are champions like Parisi and Anderson who have explored them in great details, and part of which we are talking today. So disorder, I mean, and these two disorder makes the I mean, even though they look very, very similar, except for in one case, these interactions are infinite range, in the sense that any I will interact with any j. Changes, I mean, this difference and jij are still equal. I mean, the distribution is still the same, Gaussian. What turns out that this change, the infinite range interaction versus short range interaction, makes a huge difference in the solvability of the problem. But that's a separate area. But I just wanted you to keep that in mind. Okay, so what happens when you have disorder, or even without disorder? I'm sorry. So when you have quench disorder, of course, there are randomness, and you have to deal with that we are not familiar with in physics. I mean, in traditional physics, where we talk about pristine, clean system and so on and so forth, translationally invariant. But in systems, in complex system, you often land up with what are called frustration, in this case, magnetic frustration. To understand that, we have to look into a situation where we are talking about antiferromagnetic interaction. So there is no disorder. Let's say all J are same. So you have interaction of this type, but on a triangular lattice with antiferromagnetic interaction. That means plus J. So now you can easily imagine that antiferromagnetic interactions are such that it will minimize energy going towards the ground state if the nearest neighbors are oppositely aligned. So now this is very hard to satisfy, or impossible to satisfy on a triangular lattice, because you might satisfy this bond by putting the anti-parallel spin here, but what about the third spin? So third spin can either satisfy this bond or satisfy this bond, but not both simultaneously, right? So that is also, in some senses, a broad sense. So that is what is called a frustration. And what you can imagine, frustration gives rise to multiple degeneracy. So basically, frustration lead to multiplicity of ground states. Sorry, the state is missing or is it that I cannot see? But anyway, multiplicity of ground state in the sense that all these 6 orientation of spin, which is up, down, down. I mean, here you have 2 down and 1 up, as you can see in all these 3. And here you have 2 up and 1 down. So all these 6 configurations will have the same energy. All these 6 configuration on the placket of a triangular lattice. So I mean, the fact that you can have a frustration is also strain the system. So that is also, in some broad sense, adds to disorder. So when you have a possibility of frustration, which is coming just from interaction, and there are many other interactions that can produce frustration. This is sort of one of the simplest example to see how frustration can be there. I mean, to realize frustration. So that plus disorder makes the problem very, very complex. So what kind of complexity? So that is reflected here. I mean, so sort of trying to give an idea is that you can, because of this frustration and disorder, so you can imagine that the system will lose, any system will lose the translational invariance. What is translational invariance? So that is what a homogeneous system always possesses, and that is what we normally study, that any part of the space is equivalent to any other part of the space, right? So that's the homogeneity of space and so on and so forth. So that is not true when you have disorder, because if you have disorder, I mean, certainly I mean, these two, a pair of these 2 spins are very different from these 2 pair of these 2 spins, because their JIJs are different as disorder, and also because of frustration or a combined effect. So what you land up with, if you're looking into the potential energy landscape as a function of what is called coordinates, or potential energy landscape, free energy landscape in configuration space. So that will have a very corrugated and irregular structure with many bumps and valleys. I mean, valleys in it. So that kind of a structure. So what it says is that there are many local minima. So there is a local minima, there is a local minima, there is a local minima. Their energies many times are very similar, and that's actually reflective of the fact that what I said in frustration, that there are many states which are of the same energy. So frustration does that. So there are many states which are of same energy, which are separated by large barrier. So the energy from going from local minima in configuration space to here, if you have to overcome a barrier which is given by your temperature, because so if there is a temperature, there is a thermal energy, there is a thermal kick, the system can move from one to other. However, if the barrier is large, then there is a difficulty. So the good situation is the one where you have one global minima, which is, there might be some other weak minima or maxima, it doesn't matter, but then a very clear one global minima. So that's often the case that we land up with for a homogeneous system. But in disordered system, in a glassy system, for example, this is what we land up with energy minima. So there are many possible ground states, which are the situation where the system stays in each of the local minima. And then the dynamics is very slow. By dynamics, what one means that the system jumps from being one minima to other, and so on and so forth. Maybe there is a crystal state or a ferromagnet state in this case, which is the deepest minima. That's actually the deepest minima. But then there are many other which are glassy state, and then the ideal spin glass will be the one, in case of spin language, which is the deeper of the minima other than the crystal minima. So that's basically the kind of picture one has in mind. That's what actually generates the complexity because of the disorder and the frustration. Okay, so now this was somewhat technical, and if we have survived this, then let's talk about something which is interesting.
There was a question from somebody.
Oh, okay. I'm so sorry. How do I know the question?
Yeah, so sir, just 1 second to barge in. Like Aditya, one participant just asked, sir, can you please say which topic are you discussing?
Which topic?
Oh. Yeah. It's already mentioned in the invitation. Like it's about the interplay of disorder and fluctuations in different physical systems. But yeah, can you give a very small info about the topic or the talk? Like he wants to ask or anything?
Oh, okay. information about the talk. So let me go back. So right now, what we are discussing is what are spin glasses, and so we are talking about a system of magnets. Let's say small magnet which has a polarity, meaning magnet. It will be north pole or south pole, and that's this arrow indicate. So now, if the magnets are placed on a very regular, if it is a regular magnet, meaning these magnetic moments are interacting uniformly and in a very regular background lattice, I mean, which is the skeleton that is shown here, then we know that they produce ferromagnets. So we assume that is what we know. And then if we bring in disorder and in a very irregular manner, we place those magnetic moments, then what kind of ground state could they produce? And that's what is called spin glass. So I'm trying to sort of motivate the spin glass problem. Okay. So is that in brief, is that meaningful? In broad sense, what I said is that, okay, so this year's Nobel Prize is given to groundbreaking discovery of complex systems. And one of the way to go about complex system is to study disordered system. I mean, that's a sort of a mathematical starting point. Just the way, let's say, let's say the Ising model is a prototype model starting point for understanding ferromagnet to paramagnet to ferromagnet transition. So similarly, disordered system is a nice starting point, prototype problem for understanding complex system. And within disordered physics, spin glass is a prototype model to study disordered physics. So that's the reason I came to spin glasses. Is that making sense, or?
Yeah. Thanks a lot, sir. I guess the question is been answered. Aditya, can you just confirm once? Yeah, I guess he just wrote in the chat box. It's fine.
Okay.
Thanks a lot, sir. Yeah.
Okay, thank you. Okay. So what I came to is the symmetry. So it is quite fascinating that what is symmetry, what is known as symmetry, has a very profound role in phase transitions. So symmetry, I mean, I always knew symmetry as something which is beautiful, like butterflies, right? Butterflies, I thought, were beautiful because there's a symmetry, which is a reflection symmetry, which is, I mean, to the best I can say, I mean, they're almost always exact, I mean, symmetry. And that's why they're beautiful. So the symmetry can be approximate, like you can see here the reflection of, this is also reflection symmetry of Taj Mahal on the river Yamuna. So that's an approximate symmetry. You know which one is the actual one and which one is the reflection, and so on and so forth. So what is very, very interesting, and this is a profound statement, and I won't be able to explain it in a short time, that whenever you have a phase transition, and phase transition, is something that people who like to understand matter, which are known as condensed matter physicists, broadly speaking, both classical condensed matter physics and quantum condensed matter physics. I mean, they try to understand the phases and the phase transition between them. So phase transitions are something very, very, I mean, that the word phase transition makes condensed matter physicists very excited. So it turns out that every phase transition is associated with a breaking of symmetry. So let me try to give you an example, that if you talk about a phase transition in a magnet, like here I show a horseshoe magnet with a north pole and south pole. So what happens is that in the high temperature phase, you have a paramagnet. So paramagnet is that every magnet you can consider as made up of atomic magnets, so magnetic moments which have north pole and south pole. Let's say north pole is red and south pole is green, and they are randomly oriented. So that's what makes it a paramagnet at high temperature. Now, if you cool the system, they go into what is called a ferromagnet, where each of the individual magnets line up in such a way that in generally will make a North Pole this side, this case, the way they have arranged, and South Pole this side. So you say that the system is going from a higher symmetry, meaning this is a higher symmetry than a lower symmetry. So why higher symmetry? Because you say that there is a spin rotational symmetry. Spin in this, you can consider these small magnets as a spin. So if you rotate them, the energy change hardly there is no energy change in the system. On the our ground state remains, ground state does not change. I mean, if you rotate the spins here. On the other hand, I mean, they choose a direction for the ferromagnetic alignment. So that's where the spin rotational symmetry is broken. So this is a particular, every transition will come with a breaking of a certain symmetry. And depending on this symmetry, you can define an order parameter. So like you can call the magnetization is an order parameter. Magnetization is a high temperature phase magnetization was 0. And then how much the propensity of ordering them in a nice and cool pattern is what measures the order parameter. That's called the order parameter. Now there is a small disclaimer that that every phase transition has a breaking of symmetry is not entirely true. But I will say this is certainly true for all traditional phase transitions. There are other phase transitions which people say. I mean, this is a jargon. I will use it, but I will not explain. But just a caution that topological phase transition is something about which modern scientists are very excited. So they don't come with a breaking of symmetry. But that's a very different area. So let's not talk about it. I mean, all traditional phase transitions that we know break one symmetry or the other. So the question is, the Parisi's contribution is to find out what is the order parameter for the breaking, or what is the order parameter and what is the symmetry that is broken for a transition that occurs by cooling a spin glass, which will go from a paramagnetic state to a low temperature spin glass state, which is a very, very resilient state. I mean, resilient means it's a very high rigidity. So spin glass has as high rigidity as the crystals do. However, they're still very different. They don't have a regular periodic pattern of crystals. So I'd say that. So Parisi actually had solved this model, and maybe I will talk about it a little later. Sherrington-Kirkpatrick model. So there his calculations help us understand what the order parameter is and what symmetry is breaking. But this symmetry is something which is lot more mathematical, and I must say that I don't work in this area, so I don't understand it fully. But it is quite mind-boggling, the concept behind it, and that's what is being celebrated with his Nobel, because his identification of the symmetry and its breaking seems to work in a wider area of problems in complex systems in general. So that is called a replica. I mean, so what he comes up with is called a replica trick. So what is replica? So let's say you have a glassy system like this, where particles are located like this. So this is a real glass. I mean, you can think of it as a real glass. If you change these balls by marbles by some kind of a arrow, then it will be spin glass, and so on and so forth. So now let's say you start with a box of a spin glass with a certain, everything is defined for these marbles in this system. Okay, so let's not talk about spin glass for the moment. Think of marbles inside a box. Now you compress the box and compress it identically several times. So what you make is the replica, because the particles are same and the compression size is same. So the Hamiltonian, if you want to think of, are all same. However, the configuration will be different if you compress every time, right? So that is called a replica. So this is actually quite interesting. So let me back off a bit. I mean, I thought I would say this, but I was about to forget. Is that you can so before I talk about replica. So already, if you were to solve the problem of one set like this of particles and their understanding, that is already very difficult, because there are a lot of complexities, disorder and everything which are there. So it turns out, and which is not very unusual in mathematical physics, that you think of a problem, you think of a state, mathematical state, which will make the problem seemingly more complicated. However, that in the end helps to solve the problem. So this replica trick is something similar. So you had a problem which is already very complex. So you could not solve it. I mean, you could not solve it, meaning the people who tried could not get a clue of how to proceed. So now comes Parisi, who makes the problem complicated by making many replicas. And it's not just 2 or 3 replicas. I mean, it's the millions of replicas that he creates of the same thing by compressing differently, let's say repeatedly, many times. And then, I mean, then what really works for him is that all these replicas are same in the sense that they have the same realization of disorder, because they're the same system, just compressed different times. I mean, compressing is also same. The final box size is same, and so on and so forth. So what Parisi asks is that what is the overlap of the physical properties of the system which are in different replicas? So he now takes the replica and then ask for an overlap of physical properties calculated with one replica, with the overlap of some physical property measured in one replica and another replica, pairwise. It is always pairwise. And then he look at them and look at the distribution of the overlap of the physical properties. I mean, that's called an overlap parameter. So this is technically it is a bit complex. I mean, in the sense that you start. I mean, so you have to produce some kind of a genealogical tree. So you have to make a hierarchical. There is a way to make a hierarchical classification of all the million replicas you have collected. So you start from here, and then you make some replica. From them, you make more replica, and this way you create what is called a genealogical tree. And then you take any of these replicas, or a pair of replicas from any stage of this genealogical tree, and calculate the overlap of physical properties and look at the distribution of that. It turns out that that overlap is going to work like an order parameter, the way for you the magnetization worked as an order parameter for this paramagnet to ferromagnet transition. So how that happens is far more detailed mathematics, and I mean, I don't have a full comprehension, I must agree. I don't work in that area, but that can be done. But this is the basic idea of what is known as replica trick. So what works out? So let me not get into the mathematical part of it. Let me dive into directly. Yeah, maybe this slide. So where this is the overlap I was talking about it. I mean, some Q, which is some physical property, like you look at this spin at site I and site I, but in different replica. And then you sum over all I. So alpha and beta are different replica index. And this is some average, thermodynamic average. So those are technical thing, and because I didn't talk much technicalities, so let's not go to that. But this is some overlap. So this is the physically what I described is what is that overlap. And if you calculate the overlap and you look at the distribution, you land up in the situation that in a paramagnetic state, this overlap will go to 0. So that's the order. This is actually the order parameter. Or the distribution of that acts as distribution of Q alpha betas for all alpha and beta act like an order parameter. So that will be finite in the spin glass state, and it is 0 in the paramagnetic state. So as I have written in the so there's another technical statement that in the process of arranging hierarchically all the replicas, this genealogical tree is formed, and the overlap turns out to have a property which are either self-averaging or not, depending on which phase you are. So the best way to see what symmetry is getting broken in the transition of going from a paramagnetic state to a spin glass state, you should be looking into this replica symmetry, which is certainly intuitively not obvious from the beginning. So that identification is the main contribution of Giorgio Parisi, because of which, let me go back again. Sorry, I mean I will jump many sites. So many slides. So if we come to the Serrington-Kirkpatrick model, so those mathematical tricks help Parisi to solve exactly the solution of this Serrington-Kirkpatrick model, and the ground state turned out to indeed have what is called the spin glass phase. So there are different papers which are all written between, which are here between 1979 and 83. So which actually set the stage, I mean, towards the mean field theory for the spin glass. So by the way, this is one situation in which mean field theory is exact, because it's an infinite range interaction model, but I won't go into that. That was a technical statement, and I would like to avoid technical statements as much as possible. So there are many papers, and then finally he wrote a book. So it was almost like Gibbs, I mean, who did very groundbreaking work and wrote a book instead of writing papers. Of course, Parisi wrote papers, and he wrote a book, Spin Glass Theory and Beyond. I don't have a picture of that, I'm sorry, where much of this research was documented. So finally, if you look at the phase diagram, so phase diagram, as you know, is like a map. So it's like marking territory the way you do that in maps. So similarly for different phases, like a solid to liquid, solid liquid gas phase transition, you have a phase diagram. So phase diagram as well as the phase boundary, as I said, makes this physicists very excited. So the phase diagram of, I mean, this is a schematic phase diagram for a spin glass was created. So G was the I mean, this is the coupling J, and this is J is not the coupling, but this is the width of, or the variance of the coupling of the disordered coupling. And then this side is temperature. I mean, whatever is written, don't worry. I mean, 1/2 beta. I mean, many of you will understand beta is inverse temperature, but this thing is temperature. You have these three phases, and phase boundaries were understood. So a very quick thing is that there are average of spin, and then average of spin, and then the average over all the configuration. So this is a spatial average. This you can think of a temporal average. So, and then Q is the overlap in some sense. So these three values, these three quantities when calculated gives different values for paramagnet, spin glass, and ferromagnet. For spin glass, for example, this guy is non-zero. So Q is what is called the overlap or order. This order parameter was first defined by Edward Anderson, to the best of my knowledge. So that was not Parisi's contribution, but calculating it for in the language of replicas and getting a value which is meaningfully describes the spin glass ground state is something where Parisi contributed. Okay, so this is the phase diagram, and then I should have showed this towards the beginning. I mean, the fact that spin glass exists was established long before. So there is an old review paper where you will see that. I'm not going to explain that. What is interesting, I mean, which is what I wanted to say, and it often happens for, I mean, so sort of an identity of a profound physical concept is that the effect of that pops up somewhere which is very different from the area where people started discussing those concepts. So, for example, much after all the work by Parisi in starting from 2015, people found experimental evidence of replica symmetry breaking in very different system. I mean, which is the system of random lasers, and so there are a bunch of papers, I mean, several series of papers, and people believe that people now sees replica symmetry breaking. So which started as something which is a very strong mathematical concept, is something which is realizable. So this is main thing that, I mean, these are the points that I wanted to discuss. But very quickly, if I get 5 minutes, then I will show a few slides basically to talk about to sort of show you the breadth of Paris's research. So can I take 5 more minutes? I think I have finished my time more or less.
Yeah, yes, sure, sir, sure,
Okay.
sure. You are free to use the time, anything. Yeah.
Okay, so I will
Fine.
not take too much time because it's already late. So now, as I said, that this spin glass is a subclass of what are called glass problems. So glass problem is given here. I mean, in normal glass like window glass, they're called structural glass or super cool liquid. That if you quickly cool a liquid, which could have gone into a phase transition to a crystal at this point, and that's a very sharp transition like that. But if you super cool it, I mean, if you cool it quickly, then it cannot follow. I mean, in a volume temperature phase diagram or a volume or enthalpy phase diagram, this will follow a path which is different from crystal, and it will probably never go to a crystal. It will become a high energy state only higher by limited amount, but than the crystal in energy. However, they have a very strong resilience as a state. I mean, very rigid state. Uh, and then also not only that, I mean, they will go into a glass. So this is called a glass, and you can have different glass depending on how you cool it. So this is a property of glass which is called aging. I mean, how you age, I mean, you will get different glasses. So in some sense, in the language, I'm sorry, I'm going back several slides, but that is what is encoded here. That I mean, it is a spin glass, irrespective of wherever, whichever minima you are at. They're all laboratory glass states, it's called. And then once you jump to the best one, that is the best glass state, and then there is a hope that at some point you can really go to the crystal phase. I mean, here crystals and ferromagnet and similarly regular glass and spin glass are equivalent in this picture. So you can keep jumping back and forth, bouncing back and forth between very, very different minima, all of which are glass states, and depending on how you cool it, you will go to different states, which is very different from a regular clean solid, where no matter what, you will find the ground state, I mean, which is the crystal once you cool. So in glasses, it is different, and glass I would personally consider that to be a little broader class of disordered problem, like of spin glass. Spin glass is a very nice representative starting point. So Parisi had made important contribution in this mean field theory. He tried to apply the mean field theory in glasses, I mean the structural glasses and jamming problem. And he is part of a very big collaboration called Siemens collaboration on cracking the glass problems. This is a very, very big collaboration with champion physicists in the area. So Parisi, of course, is part of that. He made important contributions. Parisi made very important contributions in other areas, which are very, very different areas and independent areas. So like growing interfaces. So how you talk about, so if you have interfaces like a surface like this, and you are putting particle and the surface grows, so how does that grow? So that is discussed by a very different universality class. So these are little loaded words, so I don't want to get into that. But Parisi, along with Carter and Zhang, came up with a description of surface growth models. So that's something which is very, very famous. So he was associated with that, which was done in 86, 86, the first paper on that. Then he was always interested in understanding climate and turbulence. Turbulence is the area which is, I guess some of you know the word turbulence. I mean, at least some notion of turbulence. So, and those of you who don't, I mean, I would say that you have done, I mean, because your students are different years. So in first year, we have a experiment which is verification of Stokes' law, where we talk about a laminar flow. So where Stokes' law for viscosity is valid. So turbulent flow is of a fluid is exactly opposite to that. That is very irregular. So that's the word imply for you when I say turbulent. So he worked on turbulence in particular multifractality in turbulence. But now I don't want to explain any of these because these are now very loaded words and jargons, and let's avoid that. But all I wanted to bring it to you that he had worked in very, very different area. He worked on climate changes, stochastic resonance in climate changes. So these are all problems of complex systems. Certainly. And then he worked on flocking of birds. So by the way, so I just wanted to bring it to your notice that if you look at the year, so this is 1982. This was done in 1984. If you could read this, this was done much later by Parisi. So this was 2000 and something, 2009. So this flocking of bird, that's a collective system of many birds which are interacting in some way among themselves, and but they make nice patterns. So he wanted to understand this starling flocks, and had a theory, had a description at least of that. So he did that. And then if you think of even before, this was done by Parisi during his PhD time, and immediately afterwards he was a trained high energy physicist. He had important contribution on what is called a pattern model, and this is a paper on quantum field theory. So many of my colleagues who are in high energy physics, they were cheering for the Nobel Prize winning of Parisi because they feel that their man has won the Nobel Prize. So at least partly their man. So that's what Parisi is. He is a person who made important contributions in many fields. And what I wanted to bring to your attention, and this is something I wanted to do because I read the year. So if you think of it, so he worked on the spin glass problem for his contribution in which he got Nobel. So that was between 79 and 83, 84, something like that. And all other different works were done more or less at the same time, except for this one. Something is 84, something is 82, and then something very different in 86. So that's quite amazing that he had been essentially worked on problems which are very different from each other, but they are interconnected by one thread, which is that they're all complex systems. So I have come. So one point that I think I must mention, that Parisi is actually quite an activist, and this is sort of I don't know if you find it interesting. It is interesting that he has a very clear and he followed his heart whenever it comes to talking against establishment. And this is an article you can read in Physics World. He had a left-leaning political philosophy, and he sticks to that every occasion, irrespective of anything, and which is a very big thing. And he stood against the government of the country where he lived for all his life, and whenever required, he had been quite vocal. So that's something I just wanted to mention. So if you want to know more, you can read, and this is quite. It is quite widely available, so for you to find out more information. So now I'm towards the very end. So I will say that it is. So this is someone else I will quote. So which is that this is another champion physicist, Charles Frank. Who in his retirement address said that said the following, that the physics is not just concerning the nature of things, but concerning the interconnectedness of all the natures of things. So no one could be a better example than Giorgio Parisi in this regard. And then I will read another quote, which is one of a long-term collaborator of Parisi. They have collaborated, and he is a colleague in La Sapienza University, Marinari, who said that Parisi has developed a paradigm that goes beyond condensed matter. his theories can be applied at all scales: glass, the brain, the finance, the flight of bloods, glaciers, and much more. So here stands our man with his arms extending from microscopic to atmospheric scale, and in a perpetual meditative state, where he is thinking deeply about uh, different incarnations of complex systems and their interconnectedness. So congratulations to Giorgio for his success, and I thank you all for your kind attention.
Thank you so much, sir. It was really informative, and I'm very sure the audience must have enjoyed it. Now, sir, sir, and the audience, sir, shall we take questions from the audience now?
Sure, please.
Yes. Okay, sir. Thank you. So now it is a request to the audience to put your questions in the chat box or in the YouTube live chat. Those who are watching us on YouTube, you can post your questions, and sir will surely address them. Thank you.
Till then, I would like to convey a very small message. Like the event is, like the talk is technically over. So first of all, we would like to, convey our heartfelt vote of thanks to today's speaker, our respected sir, Dr. Ghoshal, for his kind time and consideration in this amazing talk. Thanks to today's host, Tanishta, who managed to anchor things readily with a perpetual flow. And once again, this is the very first episode of, it is the very first Interizer event in this tenure. So we owe our gratitude to Ronak Mojumdar, who helped us stream the whole thing in YouTube on behalf of the ISA Kolkata campus radio team. And last but not the least, thanks a lot to all the audience members for joining. And yes, time for some questions. If you have some questions, you can write directly in the YouTube live stream or live chat or in this the Gmail chat box itself.
How do I get those questions? Do I have to go to YouTube?
No, sir. Actually,
Okay.
it will be visible, and we will. If there are any questions in the live chat or in the chat,
Okay, so you will tell me. Okay, so that's
yeah. Sure. Till then, we would like to, like have your views and feedback regarding this organization. Like the Science Club tried for the very first time to, organize this event, the Nobel Talk. So what was your vision regarding the same? I mean, how did you like this?
Oh, I liked it very much. I mean, more we have sessions like this, it's more we use sessions like this. I mean, we'll open up the platform for discussion, because I mean, what I really like about is a talk which is not very technical. I mean, I don't know how much I succeeded, but I tried to keep the talk less technical, because I know there are students of all different years. So it is a good idea to be able to connect among ourselves in terms of the basic basic message of a research field. So this is a very good attempt in that direction, and so I certainly appreciate it a lot. I really like this.
Yeah, thanks a lot, sir. Because like we just tried to organize a discussion session, like as you have mentioned, like discussion is important because we all are like busy amid some online life, and this is really hectic because we can't meet each other in this virtual scenario. So we tried to organize a very small platform regarding the discussion regarding the Nobel talks, which can be a bit more engaging. We can think of. Yeah. So there is a question in the chat box. Yeah, Tanishta, you can go ahead.
So yes, as you said, there is a question from Aditya Roy Chaudhary. His question is, sir, can you explain how Parisi used his idea in describing um, the flogged flight of birds?
Okay. I actually don't know the answer. I mean, I mean, these are the. Uh, uh, yeah, I can look it up. I mean, so that will be more technical part, but I don't really know. But so I would make a guess that Parisi's main tool had been this replica. So you make replica of identical systems and then uh, arrange them in some hierarchical manner, and then you look at the properties of the system by calculating overlap. So I would believe that he used this idea, and this idea is very general. This is not specific to spin glass or some other things, neural network or some school of fish or flocking bird. So I would guess that is the case, but yeah. So I'm sorry I didn't. I mean, I try to focus on the main contribution for Nobel, which is the solution in spin glass problem. The others I thought I would mention, but I don't know the technicalities.
Okay, thanks a lot.
I
I
can
guess,
try to
yeah.
find out, and I can send you a note if you are interested.
Yeah, exactly. So I guess Aditya, you have got your answer. Yeah, there is another question. Like what? Yeah, Tanishta, please. Sorry. Yeah.
Yeah, Shantan, no problem. Okay, so I'll say the question. Aditya again has asked a question that what kind of action may be used for making the replica, like compression in the glass?
Uh, uh, no, replica are essentially identical. Uh, so many times it's done numerically, and in replica trick there is a trick which is more mathematical trick, which which I might go back to. But okay, uh, so replica is identical structure which of the system which are under identical condition. Not identical structure which are under identical conditions, right? So I mean, you can so if you evolve the system, you can take the configuration at any point as replica. So that is if you are numerically evaluating replica. So now how do you produce uh, self-similar replicas is often done in numerical means. So you generate different equilibrium configurations. That will be because there is a multi system uh, of a uh, of a multi-particle system. So these particles are moving from every particles are making their own dynamics, and then there is an equilibrium dynamics which always happens. So this is certainly something which is at a finite temperature, the system which is at a finite temperature. So as a result, there is no one single ground state, right? So I mean, there are. So I don't know now to what technical level should I go, but think of the Gibbs distribution. So at a finite temperature, a system can be in many different energy states, but then all different energy states will be there with some probability, right? I mean, so which is e to the minus beta e and so on. So the equilibrium configuration possible at a given temperature of a system are could be very very different. So you can think of each of them as a replica. Now coming to replica trick, so that is something I probably can mention that. So it starts with something relatively simple because it's all analytical calculation that Parisi had done. I mean, even though he is a very very important, yeah. So here is something what is called what is the part of replica trick. So as you can see, as I have written there, that there is a I don't know. So Aditya, are you familiar with partition function? Because that is what is required for this case. So it starts with a very simple mathematical identity. You can show that this is a mathematical identity, that log of z, I can make this z to the n minus 1 divided by n. I mean, this is a mathematical identity in the limit of n tending to 0. So this is formally true for I mean, this is formally true for when n is a real number, because if it is tending to 0, it has to go very close to 0, which is a real number. But what is done, I mean, for the part of calculation, you take n to be an integer, and then what you can show from here, and this is not something that I have done. I mean, I can do here right now, but I mean, right now, meaning I can't work out the steps in between right now on board or something. But you can show that the log z being the partition function, can be written in this form, which is given in terms of z to the n. So if you wanted to calculate something, so this calculation is a lot easier. So now log of z average, there is a bar that we are seeing. So that's an averaged over averaged over all disorder configuration. So these are definitely, sorry, I mean, these are technical things. So this is harder to calculate, but z to the n is easier to calculate, because you can make replicas of various different I mean, z to the n is the case when, and if you want to average z to the n, that is relatively easier. You can make the replica, I mean, each n being a replica, and then you can do the average. But in the end, it's an analytical calculation. You put n tending to 0. So there is a way to do that. So you just consider n to be an integer, and I mean, you consider the integer n and take n to be 0, and you keep your finger crossed, hoping that the result will all work out okay. So that's roughly what I could say. I mean, so how this is done, but the actual thing is definitely more involved. I mean, yeah. So this is I would
Yeah. I guess the question is being answered also. Aditya, if you like, you can just speak up. Like, there's no issue. Okay, so you can have a vocal discussion regarding the same. And if there is no more questions from any of the audience end, then we can say that yeah, the event is technically over. We would wait for some more time. Like, let's see if there are any more questions, or then you can proceed to the conclusion.
And I think I should also mention that, I mean, if somebody is more interested, I mean, for a more detailed technical discussions, I'm always open to that. I mean, it is hard to do that now online. I mean, the calculation, but I can. So, I mean, anybody is more than welcome to write a note to me, and then when I'm in the institute, you can drop by my office and we can discuss.
Yeah, exactly. So to the respective audience, you can just like what sir had mentioned right now, you can just drop a mail to him, like contact him anytime regarding any of the issues regarding to this topic or anything else. So yeah, that's it. Sir, I guess there's no more questions from the audience end, so we can proceed to the conclusion. Like,
Okay.
once again, yeah, like our heartiest vote of thanks to Dr. Ghosal for his kind time and considerations, amazing talk. Like, once again, thanks to Tanishta, like, for hosting things quite well, and we owe our gratitude to Ronak. Like, he just helped us stream this whole thing to YouTube on behalf of the ISA Kolkata campus radio team. And thanks a lot to all the audience members for joining. And
yeah, thank you so much, and I really appreciate your effort. I mean, and for making an attempt to talk about sort of science, which is at the center stage of different subjects, in a manner which is simple and more qualitative. And I think that's something which is certainly very much appreciated. And I think that there's a great value to it. I mean, that is certainly the seeding point for more detailed technical discussions. in future. Thank you.
Yeah,
Thank
exactly.
you.
Thank you, sir.
Thank you
Thanks
to
a lot.
Science
Thanks a
Club
lot.
members and teams. And
Yeah, thanks a lot. So we can wrap it up now. So
okay.
yeah, thanks a
So
lot.
thank you. So I will then log out, right? I first.
Yeah. You all can log out. Thanks a lot.
Okay. Thank you.